Hi everybody. We're back for part 2 of our rank and null of a matrix. We're going to focus on the null and then look at some properties of both of them and then how they relate to, let's say, a system of linear equations. All right, so let's get started. So right now what you see on the screen is the definition of the null, or sometimes it's written as the nullity of a matrix. So this is a little bit different than the null space of a matrix, which uses this later. So we're not covering that yet. So basically, the null of a matrix is the number of free variables in the reduced row echelon form of A. So it's like the opposite of the rank, as we remember that the rank is the number of leading ones in the reduced row echelon form. It's the ones that don't have leading ones. All right, let's have a look at some properties. All right, so here we're going to address the relationship between our rank and our null. So if this matrix, which is like the coefficient matrix A, when we tack on the column vector of the constants B, if that is an augmented matrix with m equations and n variables, basically m rows and n columns, the rank plus the null will be equal to the number of variables. So the rank of the left side matrix, like without the B, will be the rank of that plus the null is equal to the number of columns. So obviously in a column that doesn't have a leading one, or let's say we have, obviously if we have a column that has a leading one in it, obviously if there's a leading one, there cannot be no leading ones because there's already a leading one. But one thing, what this means is, if we recall our definition for the null of a matrix, we remember that the definition of null is the number of free variables. So if we isolate for that, the number of free variables in our system of linear equations will be equal to the number of variables minus how many variables have a leading one. So that'll be minus the rank of A. So that is one way that is useful to us. So then you will have this many variables that will not have that can be any number, so that you would be, let's say you would have variable W would be equal to S, such that S is an element of the real numbers. So that, like in the general solution of that linear equation with a rank. And that kind of makes sense, because for every system of linear equations with infinitely many solutions, you would have a row of zeros at the bottom, and obviously there's no leading one there. All right, let's go on to the next property. Oops. Sorry about that. All right, so with keeping this in mind, if we have our system of linear equations and we have our coefficient matrix, which is m by n, and then we have our augmented matrix, which we have tacked on our constant vector there, the system is only consistent if the number of leading ones in the coefficient matrix is equal to the number of leading ones in the augmented matrix. So this is kind of simple. So let's say we have 1, 1, 1. Let's say this is A, and this is A with the column constant vector tacked onto it, and then, sorry, that's not right. And then our solution would be, let's say 1, 2, 3. Obviously the number of leading ones is the same Obviously, the number of leading ones in this is the same in both of them, so that means this would be the only solution to this system of linear equations. However, if, let's say, we defined A as 1, 1, 1, 0, 0, 0 in row reduced echelon form, and then we had our augmented matrix having 1, 1, actually 1, 1. Actually, let's make this one 0, even though that makes that system inconsistent. I'm just going to show that this isn't always true, but that also makes that not true while I do this. So if this was the same, but it had a 1 there, this solution does not exist at all, because you can't have 0 variable equaling 1. So that means this system cannot be solved. So that is a case where the rank of the coefficient matrix does not equal the rank of the augmented matrix. However, even if this was a 0 as well, this would not be consistent anyway, because, well, you'd have the row of completely zeros. So make sure you either have a row of completely zeros, you will get infinitely many solutions. If you have a row of all zeros and a 1 at the end, that will have no solution. Alright. So I forgot that consistent means that there is a solution. Like, obviously this is not a unique solution, however, because there are infinitely many of them, but that is a lot better than having no solution. Alright. So yeah, the definition of consistent is a system of linear equations that has at least one solution. So that's why this statement is true. So the rank of this one is 2, because there are 2 leading ones. The rank of this one is 3, because there's 1, 2, 3 leading ones. Oh, that's a lot of circles. Hang on a second. So this one has 3 leading ones, so that means, and then here at the bottom, we have a row of all zeros and then a 1 at the end. And I can't have 0x plus 0y plus 0z equaling 1. That can't really happen. That's why there's no solution. So, all right, but I can have 0 this plus 0 that plus 0 this equaling 0. So that should be fine. I have an extra 0 there. Okay. All right, I think we can move on to the next one. All right, so we have the same condition. The system is consistent for any. So the system of linear equations is consistent, so at least one solution for any column constant vector in Rm. So that will be a vector that has the same number of entries in it as the number of equations. Well, obviously, because this is like a rectangular matrix. There's not going to be like it's not going to be like that. So, but this is only true if and only if the rank of the coefficient matrix A is equal to the number of equations. So, this is, there will be at least one solution only if there is a leading one for every variable in, for every equation in our system of linear equations. Otherwise, you would get some free variables happening as well. I think I just showed that too. So those were some 3 relationships between rank and null and how they relate to the system of linear equations. So if I were to have a reduced row echelon form that had 2 leading ones and then a row of zeros, that means that the rank is not equal to the number of equations. So that means for some column constant vector, there will be one of these vectors that exists that will make the whole solution inconsistent. So obviously, if we recall what we just did, if B3 is anything that isn't 0, that means that you will get an indeterminate, or like a no solution. So if this is not 0, then this whole thing will be messed up. So that leads us back. So the number of leading ones has to be equal to the number of equations. So each equation must have a leading one. Otherwise, there exists a case where there will be a constant vector that will make the whole thing not solvable. All right, so a couple things left, and we'll get to that right now. All right, so within our augmented matrix, a system of linear equations is called underdetermined if the number of variables is greater than the number of equations, or if you have more columns than rows, right? No, more columns than rows. So if we have a look here, so if I had a system that gave me an augmented matrix of, let's say, 1, 1, minus 1, 1, minus 1, 1, and 1, minus 1, minus 3, 2, and 2, 7, obviously, no matter how much I work with this matrix to put it into row echelon form, there's obviously way too many variables for me to solve for with just this information, with just 2 equations. So since the number of variables is greater than the number of equations, this will be underdetermined, sorry. All right, so if we did put this into row reduced echelon form and it was successful, we would have a bunch of free variables. So sometimes this could give you infinitely many solutions, and sometimes that isn't helpful. All right, so now that we know that something can be underdetermined, we can also look at the case for something being overdetermined. And so on the screen, you can see that a system of linear equations is overdetermined if the number of variables is less than the number of equations. So that means we have too many equations and then a lot less variables. So let's say if I have a system of linear equations that gave me the augmented matrix -2, 1, 2, 1, -3, 4, 3, 2, and 7, with this being the constant vector, and I only had 2 variables, this would be oftentimes you would have no solution for this, because obviously this is an R2, so this is basically looking at 3 lines and seeing most of the time 3 lines don't really intersect. So, or 2 of them could intersect and then 1 of them might not. 1 of them could be parallel to the other 2. So that is not really a great case for this as well. So this one sometimes can, oops, I have my eraser on. Sometimes this can give you infinitely many, and then sometimes this can give you no solutions, but you'll still have to try and work it out with it. All right, hopefully that helps clear some stuff up and point some stuff out, and I hope that helps. Have a great day.